Hello again, Physics 20s. In today's lesson, we are going to wrap up the content for the work energy and simple harmonic motion unit of study. And we're going to continue to analyze isolated systems in this lesson. And just as a quick reminder, an isolated system is a system that only has conservative forces. Systems that have only conservative forces have no change in mechanical energy. If your mechanical energy doesn't change, we use the physics principle that's called conservation of energy. So these would be systems that don't have non-conservative forces. So a system without friction or a system without external applied forces would be an isolated system. And my starting point for a conservation of energy principle is to state that the mechanical energy at one state of interest is equal to the mechanical energy at a second state of interest. And what we're going to do today is we're going to apply this to objects that undergo simple harmonic motion. So we're actually going to go back to what we dealt with at the start of the unit, and we're going to look at conservation of mechanical energy in a pendulum earth system and also in a mass spring system. So our learning outcome is to determine quantitatively the relationships among kinetic gravitational potential. We're also going to do elastic potential there, and total mechanical energies of a mass executing simple harmonic motion. And to do this, we're going to jump straight into the examples because we already know the theory behind conservation of energy. Okay, so I have a pendulum that is 0.84 meters long, and it has a mass attached to the end of it. It tells me I raise it 0.032 meters above equilibrium and then let go. And I want to figure out what the maximum speed is. And I also want to figure out the speed of the pendulum at an in-between state. Okay, let's start off by drawing a picture, and then we're going to identify our states. So I'm going to say that this is the ceiling. And here's the pendulum. We take that pendulum and we raise it. So here, in fact, we're going to make the reference axis just go straight through the center of that pendulum bob. That's supposed to be through the center. I know it's a little bit beneath it. Okay, this value is 0.032 meters. And we're going to call that state 1. And then we let go. And then we want to calculate the maximum speed of the pendulum. Well, what position, if I'm looking at an object in simple harmonic motion, is my speed the greatest? Your speed is the greatest always at the equilibrium state. As this mass swings towards equilibrium, the restoring force is going to point towards equilibrium. So it's going to accelerate in the accelerations towards equilibrium. But as soon as you pass equilibrium, the restoring force is then opposite in direction to the direction you're moving. So then you'd slow down. So we want to look at state 2 here. So let's identify the states. So we'll say state 1. And state 1 is the furthest I'm going to get away from equilibrium. So that is your amplitude. So at your amplitude, your height is 0.032 meters. And I'm releasing it from rest, so you don't have any speed. State 2, that's equilibrium. So at equilibrium, you're on the reference axis. There's no height. And we want to figure out the maximum speed. So that's going to be the speed at state 2. That's supposed to be a 2 there. Okay, so let's apply conservation of mechanical energy. So this would tell me that the mechanical energy at state 1 is equal to the mechanical energy at state 2. Mechanical energy is the sum of kinetic and potential energy. So EK1 plus EP1 equals EK2 plus EP2. EK1, well, we don't have any speed at state 1, so get rid of that. Then EP2, we don't have any speed at the equilibrium state, so that's also gone. Yeah, this is going to be part A. Gravitational potential energy is mgh, although we need to specify h at state 1, and that would be equal to 1/2 m v2 squared. I've got an m on both in all the terms, so I get rid of it. And then just manipulate for v2. So you get v2 would then be equal to 2 times g times h1, square root of that. We'll plug the numbers in. So this would be 2 times 9.81 meters per second squared times the height at state 1, which is 0.032. And then we'd have v2 would be equal to two significant digits, 0.79 meters per second. Okay, that is part A. Now, part B wants me to figure out what is the speed at kind of like an in-between state. So I'm in between state 1 and state 2. So it could be like you've brought this up to the amplitude, you let go, and we're interested in what's going on maybe like somewhere right here. Call that state 3. Let's identify the dimension. So state 3, sorry that the string of the pendulum is so crooked. So that would be a height of 0.011 meters. And we can just identify the state here. So we can say state 3. So you need to be cautious here because at an in-between state, you actually have both potential energy because you have height. So we can say height 3 is 0.011 meters. And then we also have V3, which is what we're trying to calculate. So we have kinetic energy as well. Okay, so we could either say EM1 equals EM3 or EM2 equals EM3, conservation of mechanical energy. I'm going to do 1 equals 3 because there's an odd chance that I might have done this one incorrectly, although I didn't. But if you were actually doing it, I would always like just default back to like the information that you know at a particular state. Okay, so we are going to start off by stating the mechanical energy at state 1, which is the amplitude state, is the mechanical energy at state 3, which is the in-between state. Mechanical energy is the sum of kinetic and potential energy. So EK1 plus EP1 equals EK2 plus EP2. And at state 1, we're releasing it from rest, so we got no speed. Let's make that 0. Gravitational potential energy is mg h1. Kinetic energy, 1/2 mv2 squared plus mg h2. Got a common mass, so get rid of it in every one of the terms. And we're going to try to get v2 squared by itself, so we'll do this by subtracting gh2 from both sides. So then I'd have v2 squared over 2 would be equal to gh1 minus gh2. It's actually the same equation that we had for example 1 from last time with the falling block. Factor out the common m. And then I would have v2 is equal to 2 times g times the difference in the heights. Should point out, anytime you have a difference in heights, you this is usually an indication that you could have picked a better reference axis. So I'll come back to that in a moment. So V2 would then be equal to 2 times 9.81 meters per second squared, multiplied by H1, which is 0.032 meters, minus 0.011 meters. And then that would give me V2. Take the square root of this. Before you even do this calculation, you need to know what range it has to fall into. Well, if at the amplitude I have no speed and my maximum speed is 0.79, it's got to be somewhere between 0 and 0.79. And indeed it is. It is 0.64 meters per second. I find the biggest error that students make of these problems is they forget to take the square root when they're calculating the V. Otherwise, conservation of mechanical energy is a pretty simple physics principle to use. Now, you could have made this easier. I'm not going to show the work here, but you could have actually, in part B, changed the reference axis to being through state 3 and then redefined the height at state 1. That would have just gotten rid of the potential energy term at state 3. Oh, whoops. Now that I look at this here, I didn't put down the correct subscripts. EM3, so this should be EK3. This should be EP3. So we have 3, H2, 3, 3, 3. That's a 3. Sorry about that. Let's check that again. 3, 3, 3, 3, 3. This is a 3. This is a 3. This is a 3. That's also a 3. Okay, we've turned all the 2's into 3's. I think so. Okay, yeah. So again, if you want, you could have turned the reference axis to the location of H3. Would have made the math a bit easier, but it's not totally necessary to do. Now, there isn't a whole lot I can do to make the pendulum questions more difficult. So I'd say this is probably like the most difficult you're going to find a regular pendulum problem, excluding any challenge problems you might want to try to solve. Challenge problems are tough because like you have to use energy and you have to use dynamics as well to solve some of the information. Okay, so it says 1 meter long pendulum has a bob with a mass of 0.5015 kilograms. And what I'm going to do is I'm going to pull this to the side to an angle of 60 degrees from the vertical and then let go. Okay, so let's draw. So here's the vertical. We're going to take the pendulum, we're going to pull it a 60-degree angle towards the right. It doesn't matter which side you pull it to. Okay, this is a 60-degree angle. We're going to let go. Let's call this state 1. And then it wants to figure out the maximum speed of the pendulum. So again, the maximum speed is always at equilibrium. So that would just be, now we can just fill in these lines. This would be state 2. Okay, we'll make the reference axis through the equilibrium point because it's the lowest I go in the problem. So reference axis is where we define the height to be 0. And we have a problem here. So this is almost the same as the previous question, except the issue is I don't know what the height is. If I knew what the height was, then it'd be really easy to solve for like what the equilibrium speed is. I could use the same equation from the previous example. So what we need to do is we need to figure out what is the height. And we're just going to use some really simple trig to figure it out. Okay, here's what I know. This length here is the length of the pendulum L. This length here is also the length of the pendulum L. I'm going to draw a horizontal line from here that's going to go across and intersect that vertical line at a 90-degree angle. So I'm going to label it, make it go across like this right here. And then what I'm going to do is I'm going to use some simple trig to calculate this tiny height here. So that height's going to be y. And then to figure out what h1 would be, well, h1 would then just be the total vertical length of the pendulum, subtract the height y. So h1 would just be equal to L. So that's the distance from this pendulum here to this top position. And then subtract that distance y, which we're going to calculate. Okay, so to calculate that distance y, well, let's look at what we know in the triangle. So we have the angle 60. I want to get the adjacent side. I know the hypotenuse. That's the cosine ratio. So you'd have cosine of 60 degrees is equal to side adjacent, which is y, over L. So that's going to tell me that y is just equal to L times cosine of 60 degrees. L is 1.0 meters, the length of the pendulum, multiplied by cosine of 60 degrees. Cosine of 60, if you know your unit circle, is just 1/2. So that's going to give me y is equal to 0.50 meters. So the height 1 would then be h1, would then be the length of the pendulum, which is 1.0 meters. Subtract 0.50 meters. And then now I know what the height is, 0.50 meters. And now I'm ready to use conservation of energy. So let's go back to the purple ink color. Okay, so what do I know at my two states? State 1, that's your amplitude. So at the amplitude, h1, which we calculated at 0.50 meters. And we're releasing it from rest, so v1 is 0. And then state 2 is the equilibrium state. So at equilibrium, our reference axis passes through it, so there's no height. And then v2 would be equal to, that's what we're trying to solve. Okay, so the mechanical energy at state 1 would be equal to the mechanical energy at state 2 because we're dealing with an isolated system. So this would be EK1 plus EP1 is equal to EK2 plus EP2. Okay, at state 1, I don't have any speed, so get rid of the kinetic energy term. At state 2, I don't have any height, so get rid of the potential energy term. So it's going to turn into mg h1 is equal to 1/2 mv2 squared. I actually could have just reused the same equation from part A of example 1. It's the exact same calculation once you know what the height is. And that equation was v2 is equal to 2gh1 square root. Plug the numbers in. 2 times 9.81 meters per second squared, multiplied by h1. h1 is the height we calculated, 0.50 meters. And then v2 would be a value that is 3.1 meters per second. 2 significant digits. Okay, so not so bad once you know what the release height is, and really there's not a whole lot of geometry you need to do to calculate that. Okay, let's shift gears now to springs, which was the second example of a simple harmonic oscillator. So it says an object vibrates at the end of a horizontal spring along a frictionless horizontal surface. Again, it's important that everything's frictionless here, otherwise we could not use conservation of energy. If the maximum speed of the object is 0.35 and its maximum displacement is 0.29, figure out the mass of the object and then its speed when it's at an in-between state. Okay, let's start off by drawing a picture showing what's going on here, and then we'll worry about the math afterwards. So let's say here's a wall, and I'm going to make the equilibrium position this line. So let's say equilibrium. Now we start off with our mass located 0.29 meters away from equilibrium. So this dimension, let's do it in a different color. So from equilibrium to here would be 0.29 meters. Okay, we're going to call that state 1. Okay, so we let go. This thing's going to pass through equilibrium. So maybe it looks something like this. So we'll call that state 2. So at equilibrium, the spring's not stretched at all. And then we also have a third state we're going to worry about. We'll get into that in part C, but that's an in-between state. So it's between the equilibrium position and the amplitude. So it might be like somewhere over here. Call that 3. Okay, and this distance is 0.20 meters. Now, let's identify all of our states as much as we can. So state 1. You're releasing this from rest, so you have no speed. So V1 would be 0. Now, you have to remember, for a spring, because we're talking about elastic potential energy, your potential energy equation for a spring is actually 1/2 kx squared. So not 1/2 mv squared. Mv squared is only dealing if we have changes in height. So the important variable I want for a spring for conservation of energy is the distance from equilibrium. So in this case, it's going to be 0.29 meters. State 2. V2 is, it actually tells me the equilibrium speed, 0.35 meters per second. And the spring is unstretched at equilibrium, so x2 is 0. Okay, state 3, let's get the subscripts right this time. State 3, we're going to figure out that speed later on in part B. And the distance the spring is stretched, again, it's an in-between state, so you're going to have both kinetic and potential energy, 0.20 meters. Now, it wants you to calculate the mass, which is kind of like an odd thing to ask for. Usually, like in these problems, either you're asked for the speed at a position or like where the position is in terms of height or the distance the spring is stretched. So I'm going to have to use conservation of mechanical energy, and odds are I'm going to need to use all the information I know at 2 particular states. So I'm going to go EM1 equals EM2 because I know all the information at that, and then I'm going to hope that I can then have enough information to figure out what the mass is. So let's start off with this. We'll say A, the mechanical energy at state 1 is equal to the mechanical energy at state 2. Mechanical energy is the sum of kinetic and potential energy. So EK1 plus EP1 is equal to EK2 plus EP2. At state 1, we're releasing it from rest, so no speed. And then state 2, we're passing through equilibrium. So if the spring is unstretched, then you don't have any elastic potential energy. So EP this time around would turn into 1/2 kx squared. And we'll say 1/2 kx1 squared, because that's elastic potential energy. And that's equal to 1/2 mv2 squared. Now, when you expand any conservation of energy equation for a spring, you're not going to be able to cancel out the mass. The reason being is because the potential energy term does not have m in it. So you can't get rid of it, which is good, I guess, because we're trying to calculate the mass. But even though you can't cancel off the mass, you can cancel off something else, the 1/2s. So you should have 1/2s in all your terms. So let's get rid of the 1/2, get rid of the 1/2, and now we have kx1 squared equals mv2 squared. So we can actually solve for the mass now by dividing both sides of the equation by v2 squared. So that'd be m is equal to k x1 squared divided by the v2 squared. Plug the numbers in. Spring constant, 18 newtons per meter, multiply by the amount the spring is stretched at state 1, which is 0.29 meters squared. Divide this by the speed at equilibrium, which is 0.35 meters per second. We're going to square that. And we're going to get the mass is equal to 12 kilograms. Now, B wants me to get the speed of the object at the in-between state. So that is V3. Now, I should point out for a spring question, like you have to make the reference point the unstretched position. So it's got to be equilibrium. Don't try to mess around with where the reference point is, or you're going to get into like huge problems. Okay, so just keep this one absolutely as equilibrium where x is 0. Okay, now we're going to have to compare mechanical energy at two states. You could go EM1 equals EM3 or EM2 equals EM3. It doesn't matter because in either situation, you're going to have to use the mass that we calculated. So I'll just go 1 equals 3, although you could do 2 equals 3. So we'll state that the mechanical energy at state 1 is equal to the mechanical energy at state 3. I'm going to pick state 3 just to see if I can not mess the subscripts up again like I did in that other example. Okay, mechanical energy at state 1 is EK1 plus EP1. That is equal to EK3 plus EP3. The only term we can get rid of is the kinetic energy at state 1 because that's the amplitude. Because EM3 is, state 3 is that in-between state where you have both forms of energy. So this would then become 1/2 K x1 squared is equal to 1/2 M V3 squared plus 1/2 K x3 squared. And once again, I can cancel off all the 1/2s because they're in every single term. And again, you cannot cancel off the mass because you can see here the mass is only in a single term. So you're not going to be able to do that for a spring question. Let's get V3 squared by itself. So we're going to subtract Kx3 from both squared from both sides of the equation. So I'll have K x1 squared minus K x3 squared is equal to mv3 squared. So to get this isolated, divide both sides of the equation by the mass and take the square roots. We'd have v3 would then be equal to, we can factor this too, so this would be K x1 squared minus x3 squared, all divided by m, and we're going to take the square root of that. Plug the numbers in. So this is going to be the spring constant, which is 18 newtons per meter. Multiply by x1 is 0.29 meters squared. Subtract x3, which is 0.20 meters squared. Divide all by the mass. The mass we calculated from part A, it's 12 kilograms. And then take the square root of that. Before we even do this, we should know what the speed is going to be. So the equilibrium speed was 0.35 meters per second. So there's no way it can be that large. And it isn't. If we calculate this correctly, we should get 0.26 meters per second. That's a 6. All right, one more. Says a 3 kilogram object is located 5 meters above the ground and it's released from rest and drops onto a spring. Okay, this is a bit of a stranger type problem. Okay, so let's draw this. Okay, so let's make this the ground. We're going to say that's my reference axis. Okay, so we have a spring. And I have a mass up here, which I'm going to drop. So this is state 1. And it tells me in the problem this mass is 5 meters above the ground. Okay, so we drop it. It contacts a spring. And then the spring compresses 0.60 meters and bringing this thing to rest. Okay, so this thing's going to drop. And then it's going to compress the spring. And now this mass is on top of it. We're going to call that state 2. And the spring has been a little bit compressed. Now, we have a lot of assumptions to make here. It says, first of all, assume no mechanical energy is lost when the object contacts a spring. That is very, very unlikely. If the object hits the spring, like I would expect to hear some sound, and sound is a form of energy. But the only way you could deal with that is by implementing conservation of momentum, which is a physics 30 topic. So we're going to assume that there's no energy lost when the box hits the spring. And then 2, it says, assume the gravitational potential energy of the object while in contact with the spring is insignificant. So it's pretty much telling me that the spring gets compressed to the point where the height 2 here would be equal to 0. Okay, let's identify the states. So we're going to say state 1. Now there's 3 things I'm going to identify here. So the first thing I'm going to identify is at state 1, we're dropping it. So there's no speed. Also at state 1, I have height, gravitational potential energy, 5.00 meters. And let's identify how much the spring is compressed. Well, the spring is unstretched at state 1, so we can just leave it as that. State 2, okay, so it also says after the object hits a spring, it brings it to rest. So that's going to be V2 equals 0. It says that we can assume the gravitational potential energy is insignificant. So that's H2 is 0. So we'll assume the spring is compressed to the point where it's pretty much, the object's pretty much on the ground. And it tells me how much the spring is compressed by. So it compresses 0.600 meters. Okay, so let's go ahead and do the conservation of energy now. So I would state the mechanical energy at state 1 is equal to the mechanical energy at state 2. Again, we're assuming we're not losing any. Mechanical energy is the sum of kinetic energy plus potential energy. And this is equal to EK2 plus EP2. What can we get rid of? Well, I'm releasing it from rest, so there's no kinetic energy at state 1. And at state 2, it's also coming to rest, so no kinetic energy. This seems to be really weird because it's saying EP1 equals EP2. Now, here's where things get a bit interesting, I suppose. This EP1 and EP2 are not the same type of potential energy. The potential energy at state 1 is due to the object's position in the gravitational field. That's gravitational potential energy. So this would then turn into MgH1. You have gravitational potential energy at state 1. At state 2, well, we're not worrying about gravitational potential energy, but the spring is compressed. So that's being converted into spring potential energy or elastic potential energy, which is 1/2 K x2 squared. So a little bit of a weird energy conversion going on. We're going from potential to potential energy, but gravitational potential to elastic potential energy. Okay, let's get the spring constant isolated because that's the thing we're solving for. So K would then be 2 mgh1. Divide this by x2 squared. And then I would get K is equal to 2 times the mass, which is 3.00 kilograms, times 9.81 meters per second squared, multiplied by height 1, which is 5.00 meters. Divide this all by x2 squared. So x2 is how much the spring was compressed from its equilibrium position, 0.600 meters squared. And then we're going to get a spring constant that is 818 newtons per meter. Okay, so lots of examples. I mean, we just continue to use the same theory over and over again. And you can see like how powerful the conservation of energy physics principle is if it can extend to so many problems. And it can if you're dealing with isolated systems. Okay, so you can wrap this unit up now by completing the assignment called Energy in Pendulums and Springs, and then I will talk to you in the final unit of study for regular Physics 20, which is on mechanical waves.